excited. Today, we're really excited to have Niklas, who is a third-year PhD student at the UC Berkeley, advised by Stuart Russell and Sanjay Seshia. His research spans topics in human-AI interaction, multi-agent systems, AI safety, and formal methods. His PhD is funded by an NSF GRFP. He received his BS in computer science and mathematics from UT Austin in 2021, where he's worked at the Autonomous Systems Group under Ufuk Topçu. I hope I said that correctly, but my bad if I didn't. He also spent time at NASA Ames Research Center in the Planning and Scheduling Group with Jeremy Frank. You can learn more at his website, which we will have attached to the meeting link. Yeah, really excited to have you, and you can take it from here.
Great, thanks so much for the intro, Eugene. Thanks everybody for coming today. I'm really excited about this work, and I hope we can have a fun talk today. I greatly encourage interrupting me in the middle of the talk. I think this is it's a fun topic, and I think there's room for a lot of back and forth and discussion. So I hope we can find that today. So today I'm going to be talking about some work related to discovering how much information you need to know about other agents' policies in multi-agent games in order to play optimally. And big thank you to my collaborators, Amish, Micah, Michael, and Stuart. And I see that we've got Michael here in the call too, so maybe he can add some context and some color at some point. Cool, so let's get into it. So to start out, we're going to talk about a little bit of motivation. So to start, I want you to imagine you're driving on the road, okay? When you're driving on the road, you feel comfortable and safe driving on the road because you make certain assumptions and you have certain knowledge about the other drivers on the road. A lot of this is really very relevant knowledge. For example, you know, and you really need to know what side of the road other people are driving on so that you know which side of the road you should drive on. You need to know things like how they interpret traffic signals, right? So you know how to behave around them in a safe way. So you know what your strategy and your policy should be driving on the road. But on the other hand, there's a lot of irrelevant knowledge that you don't need to know about other drivers while driving. For example, you don't even need to know other drivers' final destination, right? You don't need to know if they're driving to Trader Joe's or Costco. You don't need to know their low-level motor controls. You just need to know the high-level decisions that they're making. You don't need to know totally irrelevant things like what radio station they like to listen to in the car. And this sort of idea is what this talk is really going to be about. So we explore the idea that in multi-agent settings, there are these strategically relevant and strategically irrelevant pieces of knowledge about other players' strategies, but only the relevant aspects are necessary to play optimally. And I'm really excited about this direction because this sounds like a simple idea, and it is a relatively simple idea, but a lot of really interesting insight and novel algorithms come out of this idea. And I think there's a lot of future work to be done in this direction too that I'm really excited about. Cool. So let's just talk a little bit about the outline of this talk. So first, we're going to discuss a few preliminaries, just set the scene a little bit and discuss some related work. Then we're going to talk about some technical motivation, introduce some definitions related to strategic relevance. And then we're going to introduce the main mathematical object in this talk, which we call the strategic equivalence relation. And this mathematical object will capture what we mean by irrelevant and minimal information. Then we're going to talk about dynamic games and how we compute the strategic equivalence relation in multi-stage, partially observed stochastic games. And then we're going to use this machinery to analyze Overcooked using strategic equivalence relations. And it'll give us a lot of insight about the types of coordination problems that arise in Overcooked and will allow us to analyze the level of complexity when it comes to coordination in these types of games. And then finally, we're going to talk about a few other applications and discuss some future work. And I hope y'all might have some feedback or ideas then, because I think there's a lot of room to innovate in this direction. Cool. Any questions about this? Okay, fantastic. So I like to sort of pull up this scale when I talk about this research, discussing the degrees of centralization and different types of multi-agent problems. And I've definitely left out some examples here, but I've just came up with a few to sort of highlight what kind of contributions reasoning about strategic information can give you in these different contexts. So on the right-hand side, on the very far end of centralization, we have ordinary multi-agent RL problems, right? We have things like algorithms like self-play and settings like centralized training and decentralized execution, which is maybe has a little bit less centralization. Then we have things like population-based methods, where you're trying to train agents to play well against a wide class of different strategies. You have things like assistance games, where you might have a robot trying to assist a human and learn its preferences, but this sort of setting is still very, very centralized. And on the other end of the spectrum, at the very extreme, we have settings like zero-shot coordination, where you've absolutely no centralization, and you're trying to learn how to come up with a strategy that can adapt with totally novel partners that you've never had any chance to interact with or don't know anything about. Similarly, we have the class of problems like ad hoc teamwork, which is similar to zero-shot coordination, but more focused on the adaptation to novel partners during test time. And I'm really excited about reasoning about strategic information because it enables new ideas and new techniques across this entire spectrum. Okay, I see somebody has a question. I'm not super familiar with this interface, so please feel free to just interrupt me.
Sure. Yeah, can you hear me fine?
That's great, yeah.
Cool. Yeah, so I was wondering, when you say like degrees of centralization, does it mean during training time or test time or both or neither?
It can mean either or both. This is it's a one-dimensional spectrum, so it's hard to pin everything accurately down on this, but I mean, this applies to both training and execution, potentially.
Okay, and
for example, please go ahead.
So in terms of centralization, do you mean in terms of like control, or do you mean in terms of sharing knowledge?
So we're especially going to be talking about sharing knowledge in this talk.
Mm-hmm. Mm-hmm.
But I think even control falls into the same setting as well. And I think the ideas we're going to talk about today apply to both settings. So I want you to have both in mind.
Cool. Thank you.
Great question. Thanks. So some of the things that reasoning about strategic information is going to enable is, oops. So first of all, it's going to let us analyze the different, in quotation marks, conventions for solving games, and allow us to hopefully generalize to different types of strategies that groups of players learn to use. And this might be applicable to generalizing across new coordination problems with novel partners. We're going to be able to design environments to specifically reduce the amount of coordination required so that agents don't need to know as many assumptions or have as much knowledge about their partners ahead of time in order to coordinate these types of problems. We're going to be able to do things like find decentralized value functions. And we're also just going to be able to compute optimal joint policies faster. So even in a totally centralized setting, reasoning about strategic information will allow us to essentially come up with a sort of abstraction that gives us better computational complexity, even in a totally centralized setting. And these should all be kind of high level right now and shouldn't totally make sense, but I want you to keep these sorts of ideas in mind as we go through the talk. Cool, okay. So let me just set the scene a little bit more. So I've discussed that these ideas apply in general sum games, and they do, but in this talk, we're going to talk specifically about coordination problems. So problems where agents have totally aligned interests, totally aligned reward functions. So I'm going to be drawing these matrix games occasionally, and I'm only going to put one number in the box because all the agents are going to share the same payoff. And the main problem in this setting, in these sort of coordination problems, is even if you know what your partner's reward function is, there's still a coordination problem, even when these payoffs are common knowledge. I mean, even in this simple matrix game here, driving on the left versus driving on the right-hand side of the road, there's really no reason that agents should choose one equilibrium over the other. And you need to decide ahead of time or have some kind of convention to break the symmetry in the problem in order to play optimally with partners. And this problem only grows in larger settings like Overcooked, where you have a much more complicated setting. Even if you know your partner is trying to help you cook the recipes, you really need to know a lot about what your partner's strategy is, and in order to coordinate well with them in these sorts of settings. And the other sort of piece of preliminary topic that I want to cover is this idea of reasoning about knowledge. We're going to be using this paradigm throughout the talk, and I think it's nice to cover this ahead of time. So the main idea here is that we're going to reason about what agents know based on the possible worlds that they can consider to be true. So what I want you to imagine is this is sort of like having a belief distribution over the state space. But instead of just having a distribution, we have just a subset of possible worlds that are consistent with what we know. So you can imagine we either know or don't know certain facts, and this allows us to have some belief over the worlds that are consistent with the knowledge that we have. So in this talk, we're specifically going to be reasoning about knowledge about other partner strategies. So on the right-hand side of the slide here, I have the policy space of all other agents. So this is what I'm reasoning about for my problem. All players negative I look at their policy space, and I want to try to learn about what kind of policies these other players can be following. So if I have no information, then the space of possible worlds that are consistent with what I know is the entire policy space. I don't know anything, so I'm not able to narrow down my partner strategy space at all. But if I learn certain facts, like for example, that others will drive on the right side of the road, then I'm able to narrow down my space of possible worlds to be consistent with some smaller subset. So here we've cut out exactly half of the policies, right? On the left, we have the policies that drive on the left-hand side of the road, and on the right, we have the policies that drive on the right-hand side of the road. So I'm able to narrow them down here. And as I learn more information, for example, if I know that others will stop at red and go at green, I'm able to narrow down the subset further. And the more information I learn, the smaller the subset becomes. So this is the sort of paradigm that we're going to be using about reasoning about what other agents know. Specifically, we're going to be using the paradigm on the right side of this slide. We're going to be reasoning about subsets of policies. And this will represent what agents know and what agents don't know. Any questions about this? Cool. Okay, fantastic. So now we can really get into the meat of it. So now we can really talk about this idea of strategic relevance. And as we go through this, I want you to imagine this, this concept that we just talked about, right? Having this subset of other partner strategies, and this subset capturing the information that agents know or don't know. So our first sort of technical concept that I'm going to introduce is this idea of strategic ambiguity. So we say a subset of co-policies, which is this object on the right-hand side of the slide, is strategically unambiguous if the entire subset induces the same best responses. So the idea here is if you have enough information so that your subset is small enough so that all of the policies in the subset require the same best response from me, then I say that that subset of policies is strategically unambiguous, because it's unambiguous what my best response should be. Yeah, please, there's a question.
Hi, would that mean if, they have the same response in all possible states?
Yes. So here when I say best response, I mean a best response policy.
Cool, I understand.
And we'll see a figure in just a few slides that will hopefully clarify a little bit more. Then there's another question, Max.
Hi, yeah. So I'm curious more about the unambiguity point, because it. Oh, my hand is going. Basically, you can still have a coordination problem based off of this point, right? Because the set of best responses can necessarily contain multiple equilibria. So despite being strategically unambiguous, it seems like there's still ambiguity about how you should behave if there are equal best responses.
Sure, yeah, but all these best responses necessarily induce the same value, right? So there's no reason we would prefer one equilibrium over the other.
Right. But yeah, anyways, I just wanted to make sure that was, it's a weird point because it's unambiguous, but it's at the same time, it doesn't actually really feel like it has that quality, if that makes sense. I don't know.
Yeah, I guess the reason we say unambiguous in this setting is that if we want to get the maximum reward, we know exactly what we need to do. Or rather, it's clear what we need to do in order to maximize a reward in that setting.
Yeah, I think I get your point. You're
yeah.
Good, thank you.
Okay, cool. We're going to be talking about this concept over the next several slides. So if more questions similar to this come up, please ask them. Cool. Okay, we'll keep going then. So the second concept I want to discuss here is this idea of sort of minimality of information. So we say one of these strategically unambiguous subsets contains no irrelevant information if adding anything to the subset makes the subset strategically ambiguous. So remember, adding something to the subset is analogous to having any less information. So this essentially tells us that this subset of information is the minimal amount of information that we can have, such that the subset of possible worlds is strategically unambiguous. This is tricky, so please ask any questions here if this doesn't make sense. Please, I see there's a question. Yeah.
Hey, so strategically unambiguous, if you have a proper subset of that, is that still strategically unambiguous?
Yes, it is. Yeah.
Okay.
Because any proper subset would induce the same best responses. So. Okay,
and then I'm just making sure that lines up with the second bullet point. Adding anything to the subset makes a subset strategically ambiguous. Oh, so yeah, that's an if condition. Subset. Oh, okay. Sorry. All right, I see. So if the latter happens, then the subset. Blah, blah, blah. Okay, sorry about that. I was kind of looking at the other direction, I think, and then I was wondering, like, wait, so if you add anything at all, then would the subset become not strategically unambiguous, even though it's a subset of a strategically unambiguous subset? So I think that's my fault. Thanks for.
I don't know. It's really confusing, and this is why I wanted to go into detail earlier, because there's this dual between knowledge that you have and subsets of policies, and the duals here go. This idea of containing no irrelevant information, they kind of go in different directions, right? The less information you have, the bigger your subset of policies is.
Yeah. Got it. Thank you.
Confusing. Cool. Yeah. Any other questions here?
Yeah. No, it's just confusing because I'm dumb.
No. It was very confusing for me too for a long time. No worries. Cool. So now we can talk about our main mathematical object in this work now, and it's going to capture these concepts that we talked about in the previous line. So we call this the strategic equivalence relation, and this is a well-defined, unique mathematical object that exists for any multi-agent game. Okay. So on the left-hand side here, we have the strategy space for all other players. Okay. And on the right-hand side, we have the strategy space for player I. So I want you to just imagine you're player I, and everybody else is all the other players. Okay. So we're going to be considering the best response mapping that maps policies on the left-hand side to policies on the right-hand side. And because the best response function is set valued, it might take one policy on the left-hand side to a subset of policies on the right. There might be multiple best responses. And one of the key ideas here is if we have two policies on the left-hand side that map to the same set valued function on the right, then these two policies differ only on strategically irrelevant details. The idea here being that if the best responses to these two strategies are the same, then they must differ on some detail that doesn't matter, right? Because we can always choose the same best response. Strategically for us, it does not matter that the agent might change its strategy from pi 1 to pi 2. And if we expand these two policies to capture all of the policies that map to this specific best response, we get an object that we call a strategic equivalence class. This is essentially all of the policies that induce a specific best response. And these policies are necessarily all strategically equivalent, meaning they're only differing on strategically irrelevant details. And if we do this for the entire policy space on the left, we get a partition of the policy space. And this partition induces what we call the strategic equivalence relation. So it gives us this equivalence relation over policies on the left, and it partitions the strategy space into these different classes that we call strategic equivalence classes. And the intuition here is that two policies that fall into the same block of the partition differ only on strategically irrelevant details like what the driving destination is. But if two policies differ on some strategically relevant detail, then they must fall into different blocks of the partition because they induce different best responses. This is the most important concept in the talk, so please ask any questions. I see you've got one already.
Hi. So I see that on the right side, you made an overlap between two of the BRs, right?
Yeah.
So you're saying it's not just one best response strategy, it's a set of them, right?
It is. Yes, we're considering the set. Exactly.
Now, as soon as you're considering the set of best response strategies for player I'm not sure how you define what you call unambiguous, the equivalence classes on the left side, because what if I'm sorry, getting confused to say it here, but what if only a subset of the best responses in that best response set are best response to that particular policy? I'm sorry if that was unclear.
Yeah, so this equivalence relation captures the sort of the most fine version of this relation that we could possibly come up with, right? We're only saying two policies are equivalent if they induce the same set of best responses. So you can imagine, for example, we could put pi 2 and pi 1 on the left-hand side together into the same block of the partition, and then just circle this overlap here between the two strategies, right? Because this overlap here is a best response for both those strategies. And this would give us a coarser version of the strategic equivalence class. But these coarser versions of the equivalence class are no longer unique. And they're still very useful, but they're slightly different concepts. And they capture very similar information. The strategic equivalence relation is just the finest version of this equivalence relation that is well-defined and unique.
And if it is the finest version, does that mean that for any of the policies in pi 1 minus I, all of the best responses in BR1 are the best responses for each and every one of those policies?
Yes, exactly. So if we go back to here, we're saying that every policy in this set here has the set on the right as a best response. So this is the set valued best response for any policy within the set on the left.
I understand. And if this were the minimal, what you call it, the minimal division to equivalent classes, does that mean that there is no other policy in the space, in the left space, that has, oh man, it's so difficult to say it, that has any best response? You know, it's so cumbersome to say it. I'm just gonna, I think I got it. Thank you.
Okay. Yeah, we can use acronyms too. SER for the relation, SEC for the classes, or you can just call it the relation, the equivalence relation, yeah, or the equivalence classes. I see we've got one more question.
Hey, yeah, so if you take the intersection between the best response for pi 1 and pi 2, does that necessitate a strategy that lands on the intersection of pi 1 and pi 2? So that would be like, in this case, just a contour?
No, so it would actually be the union of them.
Oh, interesting.
Yeah. That's why it would be a coarser partition. So there'd be fewer blocks under these if we relax the definition of what classes we consider to be equivalent. And those are very useful concepts too. This object is just the unique, finest version of the of an equivalence relation that you can come up with in this case.
Okay, gotcha.
Cool. Okay. And yeah, so quickly, just to make sure everybody got this, let's go over a quick example of what the strategic equivalence relation looks like in a simple matrix game. So here we have this common payoff game between two players, X and Y. And we want to try to compute the equivalence relation over player Y's strategy space. So on the right-hand side here, I've drawn this probability simplex over their action space. So every point in the simplex is a mixed policy over these actions. And we're interested in computing the equivalence relation from player X's perspective. So we have player Y's strategy on the left, mapping to best responses of player X. Does anybody want to try to volunteer and guess what the equivalence relation would look like in this case?
I'll try that.
Please, yeah.
All right, so we have the blue on the left would be the points for player Y, like CDE. Is that correct? And so we're essentially thinking like, all right, we have the best response to policy C would be player X's A, and the best response of policy D would be player X's B. Is that correct? To get an idea of like how to illustrate where we're drawing the best responses.
Yes, exactly.
Cool. And then yeah, best response to E would be B. That would be policy A. So I'm trying to put that as a visual, like what kind of intersections do we have? I think it's just that the intersection is between the response for C and the response for E, and then we have this little island for the response for D. Is that the right visual?
That's exactly right. Yeah. So we've got the best response of A on the top right side, best response of B on the bottom left. And then we have this green line, this one-dimensional line in the middle where A and B are both equally best responses, right? Because we're capturing this, coarsest version of the equivalence relation where we care about the set valued best response. It could be very useful to just consider, a single best response, and then maybe you could throw this green line into the blue or red region. But you'll see we have sort of this problem where should we put the green line into the red region or the blue region? Both would work just as well. So under these relaxed definitions of the equivalence relation, you no longer get a unique equivalence relation, a unique object. But thanks for volunteering. That was a great job. Cool.
My pleasure. Thank you.
So just to summarize, tying back to these definitions that we started with, the strategic equivalence relation gives us a partition of the policy space on the left into the strategically unambiguous subsets that contain no irrelevant information. And this is all done by taking the pre-image of the best response map, which will partition the policy space on the left. Cool. Okay. So we talked about how we can actually compute these things in, stochastic games. And a really important concept that relates to that is one of these results that we have in the papers. It's analogous to a Bellman backup for strategic information. The idea is that we have this result that says that two policies are strategically equivalent from some state S. And essentially what this means is in the subgame starting from state S, if the policies are strategically equivalent in the future, meaning they are strategically equivalent in the subgames that are one time step in the future, and two, induce the same immediate best response, where the best response here is over actions. So if it induces the same best response on the immediate time step. And this is the version of the theorem for fully observed settings. In, for example, DEC-POM DPs in partially observed settings, we need to reason about histories. We have a more general theorem for that, but this is the specific case of fully observed settings. So this essentially, it's analogous to a sort of value iteration Bellman backup that relates the value of some state to the state's one-time step in the future. Here we're relating the strategic information in the current state to the strategic information one-time step in the future. And this gives us this recursive relationship that's going to allow us to compute strategic equivalence relations in multi-stage games. And we can just go through a quick example of this. I wouldn't worry too much about the details here. Just try to get some high-level intuition from this. So here on the left-hand side, we have a two-stage game, okay? So the players are going to begin by choosing actions A and B. If they choose the same action, they're going to go to state 3 on the bottom right. And if they choose different actions, they're going to go up to state 2 at the top. And then they're going to play one more matrix game, okay? And they're going to get the associated values in these two boxes. And the way we now compute the strategic equivalence relation for the entire game is through backwards recursion. So we start at the end of the game and we work forwards to the beginning of the game using the Bellman backup, the recursive formulation from the previous slide to do the computations. So what we'll do is we'll compute the equivalence relations for the two final states of the game. And in each of these games, we get two equivalence classes. One caveat here is in these results that we're going to be talking about in a few slides, we only compute the equivalence relation over pure strategies. So that's why you don't see a third equivalence class where A and B are both best responses. This is mainly due to computational reasons. And also some justification that in coordination, common payoff games, there's no reason for agents to play mixed strategies. So it's more or less all right to focus on pure strategies. So after we've computed the equivalence classes for the end of the game here, we can use them to back up to the initial state of the game. And the idea is that we look at the possible equivalence classes that agents might play in the future stages of the game, and we consider the permutations of the equivalence classes that they could play and use this to compute the possible equivalence relations in the initial state of the game. And I'd just like you to take some high-level intuition away from this. I'd be happy to talk about this in more detail later on about the nuances of this. It's actually pretty important to how this algorithm works, we end up building this object called a strategic equivalence graph that sort of gives us this compressed version of the equivalence relation that relies on the Bellman backup from the previous slide to be able to reference to future equivalence relations rather than having to represent the entire policy space in each state of the game. So if anybody's curious about this, I encourage you to take a look at the paper, send me an email later. Happy to chat on a call as well. But any high-level questions about this sort of intuition here?
Yeah, just I want to clarify the notation using on the right is a little unclear to me. What's kind of this idea being used for like one set colon and then another set?
Yeah, so one of the important concepts that we're going to be relying on is that we actually compute something a little bit finer than the strategic equivalence relation. We compute this object called the valued strategic equivalence relation. And this furthermore says that two policies fall into different sets if they induce different values. Essentially because at the end of the game, we might not only care about what the best responses are, but also what kind of value following those strategies will induce. So this notation on the right-hand side says that my partner plays strategy A. And my best response is strategy A. And this will induce a value of 1.
Oh, of course. Okay. So
It's not the best notation, admittedly. And so this box over here says that whether my partner plays A or B, I can play A or B as a best response, and it will induce value 1.
Okay. No, that makes sense. Once you kind of explain it out, it actually becomes pretty clear. Thank you.
I'm glad. Good, cool. And you might be asking, down here, if you look at the game overall, you'd be like, oh, I really do want to go to the bottom right state of the game to get that value of 2. So it should matter what I do in the first state. But, if for some reason you and your partner have converged on this equilibrium where you both play B in state 3, then it doesn't matter whether you go to state 2 or 3. Right? So it's sort of an important concept here where we're capturing a suboptimal equilibrium or suboptimal strategies here. Because, another question, Eugene?
Yeah, I just have one point of clarification. Do they know what stage of the game they're in? Can they play different policies in stage 1 or stage 2? They
can, yeah.
Okay, cool. Thank you.
And in all the experiments that we're about to look at, actually, it's the case. The time is part of the state space.
Great.
Yeah. Cool. So let's jump ahead to that. If you've tuned out of the talk by this point, now is a great time to come back. We're going to be looking at some fun videos. It'll hopefully be interactive, and I think it's fun to see these results. Hopefully, I think you'll be surprised by what you see here. I know I was surprised the first time we saw these results, and I think it's really cool. So in this section, we're going to be using these ideas. So we're going to be computing strategic equivalence relations of stochastic games, and just looking at what the equivalence relations look like. So to start with, we're looking at this game Overcooked. So this is a game, we have 2 agents in this setting, and they're trying to complete various tasks to get some reward. And the reason this game is difficult is because in some settings, you have to rely on your partner to play certain strategies, or you have to coordinate with your partner to follow certain strategies to do well in the game. So in this specific setting here, and so the action space that the agents have is they can move in one of the 4 cardinal directions, or they can pick up onions and deposit them into pots. And if you're familiar with Overcooked, for simplicity, we've disabled allowing agents to put vegetables on counters or give them to their partners. It's a slightly simplified environment. So in this specific instance of Overcooked on the screen here, the agents are just trying to collect onions and put them into either of the pots. So the onions are on the right and left-hand side, and the pots are on the top and the bottom. And the tricky part of this specific environment is that the agents are trying to stay out of each other's way, right? They can't occupy the same square of the environment. Otherwise, they just bump into each other and go back to where they started. So they need to try to navigate around each other so that they can pick up the onions and put them into the pots. Yeah, that's a great question. So this is a simplified environment. The agents just get a positive reward every time an onion goes into a pot. They're not actually cooking or delivering the dishes at the end of the day. They're just putting onions into pots here. Okay, very simple. And what we find in this setting, if we compute the strategic equivalence relation in this setting for either agent, we only get 2 strategic equivalence classes. Yeah, we have a shared reward here as a team. Yeah. Both agents get a positive reward whether they or their partner put an onion in a pot. And so what we've done here is we've computed the strategic equivalence relation over the strategy space in this environment. And surprisingly, at least I think it's surprising, we only get 2 strategic equivalence classes. So essentially what that means is that you only need 1 bit of information, which of these 2 classes your partner's strategy falls into, before the game starts, in order to play optimally during the execution of the game. So we can go ahead here and actually look at some videos of what the policies in these 2 classes look like. And I want you to take a look and try to see what the distinguishing sort of fact or behavior is here that the agents are using in order to coordinate in this setting. It's a little bit tricky. Now the agents are moving a little bit fast. The time horizon here is about 8 time steps. So it's just enough time for the agents to both get 1 onion and put them in the pot. So I'll help you out a little bit here. The distinguishing factor here is that the fastest way to get to the onions is by occupying the central square in the middle first and then turning towards the onions. But of course, both agents can't do this at the same time because they can't both go to central square at the very beginning of the game at the same time. They can't occupy it. So the 1 bit of information that the agents need to exchange is which of these 2 players will get to occupy the central square first. So in the policies on the left-hand side, you'll see the green player will always go to the central square first, and then the blue player will either wait or go some other way. And on the right-hand side, the blue player will occupy the central square first. And this 1 bit of information is enough information to play optimally in this setting. And one of the sort of intuitions that we like to, we actually never use the word conventions in the paper, but we do think that the different blocks of the strategic equivalence relation, the different partitions, pretty cleanly capture the sort of conventions that you can follow for solving a game. And if you'd like to, discuss if that kind of captures your intuition of conventions or not, be happy to chat about that. And any questions about this specific setting here and how we got the equivalent relations and where they come from? Yeah, please.
I would also think about what happens with all the incompetence policies. I mean, we are seeing here policies that work well. What happens with all the policies just walk into the wall without doing anything?
Yeah, so specifically here we've computed the equivalence relation over non-dominated strategies. So we're assuming some competence from our partner. If our partner is potentially adversarial, the equivalence relation might look a little bit different.
Okay, I understand.
Yeah, that's a great question. And we're also assuming here that agents can play optimally, so that they're able to do perfect best responses. And the partitioning only comes from these differences in perfect best responses. Yeah, another question, Dave?
Yeah, so in this case, like I realize this is a very simplified environment, but this two classes of strategic equivalence that you talked about, do you think this is like a direct, like comes directly from the fact that there's like two pots and two agents and very limited actions? Like if there were multiple pots, would there be multiple different classes of strategic equivalence?
So maybe hold your question until the next slide.
Okay. I figured the environments were going to ramp up, but yeah, thanks.
Yeah.
I have a quick question. So it seems like this is oddly a form of fictitious play that doesn't actually use what fictitious play is intended to like mainly use, which is trying to optimize based on the distribution of past actions by an opponent. So it seems like a cooperative fictitious play setting because it's still doing what's optimal in response to like information about what the cooperator wants to do, but no like actual empirical distribution of what the cooperator has done in the past, because it has to start from state 0, right?
Yeah. So the way I like to think about this is the strategic equivalence relation tells you how many bits and what type of information you need to exchange before the game begins in order to play optimally.
Interesting. Yeah.
Once the game starts, you can observe your partner's behavior and respond. And you might argue that observing what your partner is doing during the game and learning during the game, perhaps, is another form of coordination. But we're specifically looking at how much information agents need to exchange ahead of time. So these, you can think of them as the conventions that agents were able to converge to ahead of time, or if agents had some information channel that they were able to transmit something over. Or these agents are out in nature and they naturally converge to some equilibrium, then they've already intrinsically exchanged some information over a long period of time to converge on that equilibrium.
Okay.
So I think the next example is pretty insightful. So let's take a look at that. So yeah, just to summarize here, we've got two classes characterized by which agent gets to occupy the central square first here. So here we have this slightly more complicated environment. So again, we have two agents here, but now we also have some tomatoes. And the agents get a positive reward for depositing a tomato and an onion in the same pot. So we got multiple pots. The agents here, they're constrained by the central pillar and they can't pass through each other. So they have to be able to coordinate to get around this pillar. And then, they need to split up which agent gets which vegetable and which pot they use. So I want you to take a second and try to compute or guess how many equivalence relations you expect to find in this environment. How many equivalence classes, rather? Anybody want to volunteer a guess?
I guess 4.
Okay, I like that. How did you get that?
So you could get 2 from essentially like the symmetry of just the agents could each like be going to the corner and coming back on the same side of the square as they're getting vegetables. And then you have the 2 agents could be going in a circle in either direction and also be having an equivalent, essentially an equivalent strategy where they're able to pick up and then bring back to the baskets. Okay,
I like that. What about which agent gets which vegetable or which pot they use?
Ooh, I forgot about the vegetable asymmetry. Can I just double 4 into 8 because they could each get each vegetable?
Yeah, I think that's reasonable. Yeah.
Cool. All right. Now
Anybody have any other ideas?
Does it take an additional state just to turn direction?
It does, yeah, to rotate.
So, okay. So it's like not necessarily doubling every single time. In certain cases, depending on what direction you're going into the bucket, like say you're going from top to right, then the right bucket is the one that you'd want to put it in, because it'd be an additional state to go and turn and put it into the top one.
Yeah,
I presume. So I can't do the math because there's a lot of times twos and times ones.
Yeah.
And that's very difficult for me. So
I'll save you some work. Okay.
there's not many. I'm just kidding. We love exponents of two. Computer scientists.
So the math is very simple, because there's only one strategic equivalence relation. Sorry, class. One strategic equivalence class. Okay. So what this means is actually you don't need any information. You don't need any knowledge of your partner's strategy before the game starts in order to play optimally. And we were really surprised when we saw this result. And I think this is really cool. Almost everybody says 12 or 8 or 4 classes or something. And that's originally what I guessed too. But it turns out that the fact that Overcooked is fully observed means that the observations you make during the game gives you enough information and enough time to react to what your partner is doing, and you can still play optimally. So you can see here, the green agent always goes to the vegetables first. And whether they pick up the onions or the tomatoes, the blue agent can just pick up the opposite, right? They don't need to agree on that fact ahead of time. And whether the green agent goes, down to the right or back up to the left or whatever way they get around the pillar, the blue agent can respond accordingly. And whichever pot they end up depositing in the top right, the blue agent can respond. It devolves into this sort of leader-follower relationship.
So they both need to.
Oh yeah, please go ahead.
No, I'm sorry about that. I just wanted to clarify. They both need to put the vegetables in the same pot, and I might have missed you saying that earlier.
Yeah, they do have to put the vegetables in the same pot. That's right.
Okay, and if they didn't, then do you see very quickly, since you probably would see very quickly, that there would be more than one strategic equivalence relationship?
No. There'd still just be one, because it doesn't change what your best response would be. So the high level takeaway here is that you don't need any information before this game starts about your partner's strategy. You don't need any assumptions. You don't need to know whether they drive on the right hand side of the road or how they interpret traffic signals or anything like that. And you can play optimally with them during the execution of the game.
So it's a best response strategy now, and that could include different actions potentially within a state, but it's still like, since we're talking about strategies, we're not really looking at like that granular of a level of fine tuning, because again, like let's say that you could put it in 2 different pots, then it'd be a different action, but the strategy's the same. Exactly
right. The strategy is conditioned on the state, so it's able to behave differently in those different settings. That's a great observation.
We're approaching the end of the talk, so I'm just going to ask to pause questions for a second so that we can give you a chance to wrap up.
Okay, yeah. I'll just take a few minutes to wrap up here. So we have this other environment here, and the main point here is that if the agents here can see what their partner's doing, if the environment is fully observed, like ordinary Overcooked, we get 2 equivalence classes. But sort of what you'd expect is, as soon as we make the environment partially observed, and the agents can no longer see what their partner is doing, which way they're facing or what they're holding, the number of equivalence classes blows up. And I think this sort of matches the intuition that in partially observed environments, you need to make more assumptions, or you need to communicate more with your partner ahead of time, because you can't rely on observations, and the level of coordination goes up. So sort of the reason that the number of equivalence classes is so small in Overcooked is largely because the environment is fully observed. and you actually don't need to exchange that much information ahead of time. And leads me into one of my points that overcooked is sort of easy when it comes to coordination. And I think our formal analysis using equivalence relations backs up that point. And the idea is that if there are very few strategic equivalence classes, it means you don't need to know very much about your partner's strategy, which means you're going to get results like this, right? Where you're able to collaborate with humans in Overcooked without human data. This basically means that you actually don't need to know that much about what your partner's strategy is, and you can still play a best response in Overcooked. Because there aren't that many strategic equivalence classes, you don't actually need to distinguish between the possible strategies that the human could be playing. So we've got some other results, like saying that using strategic equivalence relations allows us to do policy space compression and policy space abstraction. That gives us some really nice computational speedups for computing optimal strategies in these settings. So we essentially took the state-of-the-art algorithms for finding optimal strategies in DECPOM DPs, and we just put strategic equivalence relations on top of them, and we got some really nice speedups. And just to wrap up, I think there are some really exciting future directions for reasoning about strategic information. Things that are simple as communicating over a limited channel, so trying to figure out what kind of bits of information you should exchange, to things like active learning in coordination settings, or learning conventions that particular agents are using from data and using that to generalize, as well as many more topics. So with that, I'll end my talk, and please reach out to me with any questions, or if you'd like to chat at some point. I'm really excited about this work and really excited about all these future directions. I encourage you to take a look at the paper and the videos on our website as well. Thanks, everybody.
That was a really great talk. I think we have time for one question before people start logging off, and then I'm going to pause the recording now.